Hi everyone, welcome back to the Med Student Notes. There is this table in first aid which talks about the partial pressure of oxygen and oxygen saturation in different conditions, and I'm going to be breaking this table down. And even if you're not doing USMLE, if it's NEET, or even if you're in your med school, I think this video is going to be super helpful, and it's really important because sometimes you just tend to memorize these things and that's not going to help you. Anyway, I want to, as usual, get right into the basics before we start everything else. A gentle picture of the layout. We've got the lungs and the heart, and there's a little snapshot of the lungs with the alveoli capillary interface. And right here is a snapshot of the blood itself. And these little flower like structures I've made is basically a schematic of hemoglobin. Now, you remember that hemoglobin consists of 4 globin chains, alpha 1, alpha 2, beta 1, beta 2, and each of these chains contains a ferrous ion. I want you to assume that that little yellow smudge is a ferrous ion, and each of these ferrous ions will bind to an oxygen. This is the normal hemoglobin structure. Correct? So each hemoglobin has 4 chains, alpha 1, alpha 2, beta 1, beta 2. Each chain contains a ferrous ion bound to heme. This red part thing is the heme. And each ion binds to an oxygen molecule, right? This is how oxygen travels in the blood and is supplied to your organs. Okay, that's the general layout. Now, what is oxygen dissolved in plasma? Once you breathe in, from the alveoli, oxygen enters, and there's going to be some amount of oxygen that's going to be dissolved in the plasma. Not bound to hemoglobin, but dissolved in the plasma. It's lying around outside here. Okay, so basically, partial pressure of a gas is going to be something that it exerts against like the walls of the container that it is in when it is unbound. The oxygen here is bound to this hemoglobin molecule, right? So it's kind of trapped inside it and it's not going to go and collide with the walls of the vessel. The pressure that is being exerted by oxygen is only going to be the oxygen that is free, not bound to hemoglobin, and that is traveling freely in the plasma. And that is your PaO2. Just the oxygen dissolved in plasma, which is free and unbound. This PaO2 is what you measure when you do an ABG, an arterial blood gas analysis. And you know the value that you get when you use a pulse oximeter on patients, and in a healthy patient you get like a 98, 99. That is actually oxygen saturation. This is pressure, right? It's measured in millimeters of mercury. This is basically a ratio. Saturation of oxygen. Basically, it's the amount of oxygen that is bound to hemoglobin. The amount of oxygen bound to hemoglobin, right? So this is oxygenated hemoglobin divided by oxygenated hemoglobin plus deoxygenated hemoglobin. It's going to be measured in percentage. So now that we've got that clear and out of the way, let's discuss what happens in different conditions. What happens in anemia? In anemia, the root problem is your hemoglobin goes down, correct? So let's look at the other values here. If your hemoglobin goes down, is this oxygen going to change the unbound oxygen that is free in the plasma? No, that's not going to change. So your PaO2 is going to stay normal. Now, SaO2. This can be tricky for some students, so I'm going to take a little detour and talk about this, okay? See, imagine there are 3 party halls, okay? Each party hall can fit only 10 people. Percentage saturation is basically the measure of how many people this party hall can fit, right? If I am taking out a party hall, is the amount of people that the other party halls can fit, is that changing? No, right? It's staying the same. There's a party hall that's disappearing, but the remaining party halls, they can still fit 10 people. This is a simple metaphor for your percentage saturation. If your hemoglobin molecules are disappearing, okay, this one hemoglobin molecule is vanishing. But is the amount of oxygen that can bind to this remaining hemoglobin changing? No. This hemoglobin can still accommodate 4 oxygen molecules. This hemoglobin can still accommodate 4 oxygen molecules. And even if you want to see it in a mathematical way here, if your hemoglobin here decreases, all of it is going to decrease, right? And in ratios, when your numerator also decreases, your denominator also decreases, your ratio is not going to see much of a change, is it? So, saturation of oxygen is going to be normal because the amount of oxygen that is bound to hemoglobin is going to stay the same, although hemoglobin itself is decreasing. I hope that that was very, very clear for you. You want to remember that most of the oxygen in the body is bound only. There's a very small amount of oxygen that is lying free. Most of it is bound to hemoglobin. So when you receive oxygen from your alveoli, hemoglobin is binding to it and taking it in. Only a certain amount of oxygen is going to be dissolving and floating freely. Most of it is going to bind to hemoglobin. So the more hemoglobin you have, the more oxygen content you're going to have. If you have less hemoglobin, this amount of oxygen that is going to be dissolved, there's not going to be much of a difference in that. But your total oxygen content is going to decrease because you don't have enough hemoglobin molecule to take majority of the oxygen, right? So your total oxygen is going to decrease. Now, polycythemia is kind of the same thing but in reverse. Here, your hemoglobin is going to increase, yeah, right? But your partial pressure of oxygen is going to be normal because this is not going to make any difference in this unbound oxygen. And same thing with oxygen saturation also. It's going to stay the same because the amount of oxygen that hemoglobin can bind is going to stay the same, although the amount of hemoglobin itself is increasing. And because the amount of hemoglobin is increasing, your total oxygen will increase again. Because you have more hemoglobin molecules, you can take more oxygen into the body, right? So that's how that works. Let's now move on to carbon monoxide poisoning. Now, in carbon monoxide poisoning, you're basically breathing in carbon monoxide. And this carbon monoxide is being taken up by the hemoglobin. Carbon monoxide is a very sneaky little thing, okay? It'll come in, it'll knock out this oxygen because this has way more affinity to the ferrous ion here. So, carbon monoxide is going to attach itself to the hemoglobin. And now there's going to be some oxygen that is already here, right? The oxygen that it has not knocked off, the presence of carbon monoxide is going to make this ferrous ion hold on to the oxygen tightly. It's like, I don't want to leave my oxygen. If I leave my oxygen, carbon monoxide is going to come in, so I don't want to do that. So not only is this displacing oxygen from its place, it's also making the existing oxygen and ferrous ion hold on to each other more tightly. So what's happening here ultimately when you come into the circulation and you want to supply oxygen to the body, first of all, there's less oxygen, right? Because hemoglobin has more carbon monoxide bound to it. And second of all, the oxygen that's already in the hemoglobin, that is also not being released. So in this horrible situation, what would our stats be like? Partial pressure of oxygen. Again, the amount of unbound oxygen happily floating in the blood. This guy is unbothered. This guy doesn't care. That's not going to change. So your partial pressure, normal. Hemoglobin. Hemoglobin is the same, right? What's happening to the amount of oxygen bound to hemoglobin? Truly, it is decreasing, right? Because carbon monoxide is bound to places where oxygen should be bound, the amount of oxygen a hemoglobin molecule can hold is decreasing. It's not holding on to the 4 oxygen molecules that it generally can. So your oxygen saturation is decreasing. But the problem here is it can look normal on pulse oximeter, because your pulse oximeter can be duped. It is going to see bound hemoglobin and assume that it is hemoglobin that is bound to oxygen, but in actuality a lot of it is bound to carbon monoxide, so your oxygen sats can appear normal. In fact, they can also be around 85% to normal. Okay, what happens to total oxygen? Now, it should be quite obvious that total oxygen content is decreasing. Now you have oxygen here and you have carbon monoxide here. Your hemoglobin is pulling on to carbon monoxide rather than oxygen because more affinity, right? So the amount of oxygen uptake is only going to decrease because carbon monoxide is going to be coming inside. So your total oxygen in the blood is going to decrease. I'm going to make a part 2 video to explain methemoglobinemia and cyanide poisoning. I hope you liked this video. I had a little bit of fun with the sitcom gifs and little references. I hope the content was really useful and you actually learned something. If you did, please like, share, subscribe, and comment. And thank you so much for watching. Bye bye.